Why does the same neutron seem to live for two different lengths of time, depending on how we measure it? In the energy filament theory, that mismatch is not just an experimental headache. It is the third close-up hint that particles are not dead hardware but evolving filament structures that react to their environment. Earlier in this series we met two clues: atomic clock drift, where electron rhythms shift slightly with changes in tension, and the proton radius puzzle, where the same proton looks a little bigger to electrons and a little smaller to heavier cousin electrons called muons. Now the neutron steps onto the stage with its own anomaly. Textbooks ask a simple question: how long does a free neutron live before it decays? In this picture, a proton is a 3-loop filament knot with 3 tension bridges all pushing outward, like 3 poles holding a tent upright in a very stable way. While a neutron is almost the same structure but with one bridge flipped so it pulls inward instead of out. That flipped bridge turns the neutron into a crooked tent that is still standing but always straining and especially sensitive to any changes in the surrounding energy sea. Experimentalists attack the lifetime into classic ways. In the bottle method, they corral a cloud of neutrons inside an invisible bottle made of magnetic fields, gravity and walls, wait for a while and count how many are left. From the fractions that survive they infer a lifetime. And in that setup the neutron seems to die sooner. In the beam method they send a stream of neutrons through a detector like water through a pipe, and do not count neutrons directly. Instead they count the electrons and protons produced by decays in flight and work backwards from those numbers. And in that configuration the neutron seems to live a little longer. Both approaches have been refined for decades with new labs, new hardware and new analyses. Yet their answers still differ by roughly 10 seconds on a total lifetime of only about 15 minutes. That is already a few percent, which in precision particle physics is not a smudge after the decimal point, but a crack in how we picture the object itself. Mainstream physics so far treats the gap as systematics. Maybe some neutrons quietly escape the bottle without decaying. Maybe the beam method hides small backgrounds. And in the future, cleaner experiments will close the gap. This view does not deny that. But it also takes the filament picture seriously and asks a different question. What if both experimental scales are mostly honest, and the neutrons they see are not quite identical because that flipped bridge, being marginal, holds out for slightly different times in different tension environments? You can picture it as a tent with one pole braced at the wrong angle. The frame is in awkward balance, not collapsing immediately but always under internal stress. In the bottling method, the neutrons sit in a fixed pattern of fields and boundaries, and that reversed bridge is held in one particular way all the time, like the tent standing in the same yard with the same wind direction. So the hidden fatigue that breaks the structure shows up a bit earlier. In the beam method, neutrons are flying through space, sampling a different pattern of tension and fields. The reversed bridge feels forces with a different timing and direction. Some disturbances average out along the path and the same kind of barely balanced tent, and last a little longer before it collapses. In this view the neutron is not misbehaving at random. It is a built-in edge of stability state. More sensitive to tension than a proton but not as fragile as a very short-lived particle. And its flipped bridge quietly adjusts its hold time when the surrounding sea changes how hard it is being pulled. If particles were perfectly rigid steel parts whose interiors ignored their environment, then no matter how clever our setups, bottle and beam methods, once corrected for obvious biases, would be forced to converge on a single lifetime and the remaining spread would fade into known error bars. Instead, the bottle lifetime and beam lifetime tracks have marched side by side for decades without meetings. As if repeating the same message, a neutron is not just a broken proton. It is a tension-sensitive balance point that answers a change in the sea, changing how long it can hold itself together. In this language, the neutron lifetime anomaly strengthens one overarching conclusion: particles do evolve, and different internal structures respond to tension in completely different ways. Electrons respond with timing, protons with size, and neutrons with lifetime, while other particles speak through tiny shifts in magnetism or in spectral lines that quietly drift off key. Tap follow, share it on New Physics, Clear Universe.